welcome everyone to the midterm evaluation of Chadi. It's already a bit longer the PhD studies than the midterm literally, but COVID was trying to so that this midterm evaluation. There was an idea that you come actually last semester already to the midterm here, but yeah, this COVID rights and rules and
just so
you do it a bit later, but that has also the benefit that you pass in front is shorter, so towards the end. And yeah, we will have, let's say, 25 minutes talk and then more Q&A from, let's say, the evaluators and also from the member of the graduation committee, who is represented by Matthias Vogt today, stepping in. And yeah, the doctoral committee members is me and Sigfrid Brynjolfsson sitting over there. And Sebastian, you can hear me? And online, Dr. Med Sebastian Fritsch, that you should see, who is also in the doctoral committee. So I'm diving into this. Go ahead.
Okay. So thank you all for joining. Thank you, Sebastian, for taking time off your schedule. And I think we can start, if the pointer allows me to. Apparently not. Okay, well, we can do this the old-fashioned way. So welcome to my presentation. My thesis is based around the idea of the design and evaluation of parallel and scalable machine learning applications in biomedical modeling applications. We are really good at naming things. So my name is Chadi Barakat. We are I am today presenting my midterm evaluation for the PhD, and the doctoral committee, as Morris mentioned, are himself, Professor Dr. Engineer Morris Riedel, Professor Sigurður Brynjolfsson, and Dr. Med Sebastian Fritsch. Oh, now it works. So to start with, I am going to go through the process of explaining why we're doing the work that we're doing. And this, mostly the motivation behind the work that I'm doing is mostly based on since it's a medical project and it's an application of machine learning and high performance computing in this field. So mostly the whole idea is based around the disease acute respiratory distress syndrome, which is a medical condition that affects a significant fraction of intensive care unit patients, and it has a very, very high mortality rate. In some research, it is 40%. In some research, it's mentioned that it's about 50% of affected ICU patients. It's generally represented as, in this case, these are X-ray images of the same patient before, during and after ARDS recovery. In this case, it is visible that they have this kind of opacity in the lungs, where it's described as ground glass. And this is mostly because either alveoli are collapsing or there are, as they call it, they mention it here. No, they don't mention it, but they are things being introduced into the lungs, either water, mucus, blood, or just the tissue itself breaking down. With that in mind, this is a significantly dangerous condition, and it's due to several causes, including indirect injury and direct injury. Direct injury including persons in fire, inhaling smoke, or inhaling dust that can scratch glass dust, which is a condition that a lot of people who work in buildings have to deal with. There are also conditions in accidents, drowning, toxic inhalation, and direct injury can be due to mechanical ventilation, where we are trying to save the patient, but by doing so, introducing pressure into the lungs, it can cause lung damage. So it is characterized by bronchoalveolar injury and alveolar collapse. This is the word I was looking for, which is called bilateral infiltrates in the lungs. So it's either in both lungs or in one of them, but in both cases, it is dangerous to their health because it reduces the amount of oxygen that can be introduced into the blood. The disease is mostly dangerous also because it kind of degrades very quickly. So mostly the earlier we detect it, the better, the more likely we have positive outcomes for the patient. So if we detect it as early as possible, which is what we are trying to do, we can mostly guarantee that the patient either comes out of it healthy or at least on the way to a recovery in a certain way or form. So mostly the consensus right now is to diagnose ARDS based on the Berlin definition, which is a guideline that a lot of hospitals do not exactly follow by the letter, or if they do follow it, they do not, it does not specify a specific duration for how the diagnosis happens. The diagnosis mostly happens with a ratio of blood oxygen to ventilation of 300 or less. If that patient satisfies these conditions, they are considered as ARDS, and the lower it is, the more severe the condition is. But it does not specify specifically how long that patient needs to be in that status. So with that in mind, we also have to think about the medical applications of machine learning, which is common enough to have a list like the one on the we can see on the slide here, which was compiled by Lundervold and Lundervold. They specify different applications of machine learning in healthcare, and they are applications in the brain, in the kidney, prostate, spine. All of these are just in that list, but there are of course many others. And their list is definitely not comprehensive, since we already also know different applications that I have at least read about during the beginning of my PhD. On the other hand, Das et al. And Wang et al. Separately work on simulation models for the cardiovascular and respiratory systems, which are either mechanistic models or machine learning models, both of which are applications of computers, data science, and to a certain extent, a more advanced level of computing for the study of medical data and medical conditions. And finally, Huddar et al. And Mayer et al. Discuss the prediction over clinical data using ML models. Specifically, I think Huddar et al. Used recursive neural networks and natural language processing to analyze notes made by doctors during the ICU stay of a specific patient in order to help in diagnosis or in treatment direction. But none of these applications were directly used in terms of help, in terms of assistance or like making decisions. It was more like pushing or suggesting treatment applications. Finally, we talk about high-performance computing and machine learning, because in the last years, we've been hearing a lot about machine learning applications, AI, and deep learning accelerating due to the increase in size of processors or their capacity to hold data or their capacity to analyze data. And at the same time, high-performance computing itself is becoming more accessible to more people with cloud computing, with access through cloud vendors or private vendors. So they're becoming more commonplace. And Goetz et al. And Wang et al. Separately talk about parallel implementations of BB-scan, which is a machine learning algorithm. Goetz et al., of course, the et al. Here considers maybe 3 people in the room as well. I also mentioned Ertlingson and Sedona et al., who are also present in the room, because they also work a lot on machine learning in high-performance computing. Their applications are for remote sensing, but of course, these are also applications that can be ported, because the knowledge is almost the same, it's just different applications. And I specifically mention here 3 separate parts of the compute nodes that we're using, which are on the deep supercomputer. And we can see the access to many CPUs. And at the same time, these also are backed by GPUs. So acceleration can be in 2 different directions, where CPU are for more computational intensive applications, but GPU are more for, let's say, large-scale matrices, or they are better at dealing with matrices. And on this side, we have 2 charts from Sedona et al. From the paper they recently published, where they show how acceleration happened with scale-up. In this case, how many tasks per node, so how many on each node, how many GPUs are being used, and on this slide, how many nodes in total are being used. So as you can see, the acceleration is limited in a way, but also the growth of nodes kind of does not exactly show how the growth is happening. But if you look at doubling, so speed is doubling by like time reduction is doubling, while the number of GPU nodes is doubling. So from 500 to 150, 120, 60, and I can guess that 32 would be 30. So with that in mind, we come to the main project, the overarching project that my PhD is part of, which is the Smart Medical Information Technology for Healthcare, the SMITH project, which is one of the 4 consortia of the Medical Informatics Initiative in Germany. This is a project funded by the German Health Ministry, and it aims to establish the infrastructure for research in healthcare. This infrastructure is mostly to define the governance for this structure, but also to determine how the communication and data sharing of medical information is going to happen between research institutions in Germany. These would be university hospitals, universities, research centers like the Forschungszentrum Jülich, which I am a part of, and with also pharma companies, mostly one company, which is Bayer. The SMITH project has 2 clinical use cases and 1 non-clinical use case, which kind of oversees these 2 use cases. I will not mention it because it's a bit broad and hand-wavy, but the one I am interested in, which I am part of, is the algorithmic surveillance of ICU patients. The HELP use case is mostly taking care of bloodstream infections like sepsis and others, but mostly concentrating on sepsis and then branching out into others. But the algorithmic surveillance of ICU patients is mostly concerned with using algorithms, machine learning or not, in order to help in ICU patient diagnosis, kind of direct the diagnosis process or narrow it down in a way or another. With that, we come to the problem statements and the suggested solutions that are offered through my PhD work. So ARDS is one of the major application fields in the ASIC use case. It is mostly the thing that we are trying to concentrate the most on, but also since it is a lung condition, there are several lung conditions that can be branched out into through the research that we are doing. But the first challenge in this, as I mentioned before, is that the Berlin definition aids diagnosis, but it does not specifically define the terms by which diagnosis is happening. So every ICU differently diagnoses ARDS or applies the Berlin definition. This is due to either the chief medical doctor in the ICU being either more experienced or less experienced in that with that specific condition, or whether it is specifically something that they are capable of dealing with, or just like a condition that happens less often than normal. Recently, I had a conversation with Konstantin Sharafuddinov, who is also one of the University of Aachen PhDs who's working on ARDS. And he noticed in his data that patients that were diagnosed with ARDS in the 90s are far less in number than the patients diagnosed with ARDS in the 2010s, 2020s now, mostly because of the Berlin definition, but also because doctors in the ICU are more aware that it might happen. Otherwise, they would have called it by different names, or they wouldn't even have diagnosed it. They would have just tried to tweak some values in the ventilation parameters. With that in mind, speaking about tweaking, there is also no consensus on how to treat, because in some of the papers, including Das et al. And other researchers, Das et al. At least did 2 papers about the optimal treating strategies. Some of them that slightly contradict each other. One of them speaking about high PEEP, low tidal volume. Some of them speaking about maintained ventilation, or mostly their papers are about lung recruitment maneuvers, which are trying to coax the lungs into opening slowly without trying to induce more lung injury. But at the same time, there is no consensus. None of these papers are 100% sure that this treatment is going to work and another will not. And finally, there is a lot of clinical data, especially with the introduction of electronic health records. All of the hospitals in the world have access to a certain type of electronic health records, but not all of them have enough resources in terms of manpower or compute power to be able to process all of this data. So the other challenge that we face is that medical staff do not necessarily need to deal with this data. they need to extract the information from it, but we cannot expect them to learn machine learning in the first place, or even before machine learning to learn programming, then to learn machine learning, then to apply it using high performance computing to be able to process the data and extract some information. So this is where we come in as researchers in biomedical applications with access to high performance computing. We can do all of this work with the basic knowledge that we have of medical conditions, with experience that we have by sharing information with medical doctors, with pharma companies, with institutions, and with professionals in machine learning. We can apply HPC and machine learning in using the data provided through the collaborations in the Smith project. We also have access through our partners to a simulator, which is a MATLAB-based simulator, a mechanistic-ish model, kind of old, but also using several papers, it was verified that it is functional, accurate, and predicts outcomes of patients in a similar way to what is real. So through one of the project partners, we have access to this simulator, and we have access to the HPC resources through the ULISH Supercomputing Center. So might as well bring them together, try to port them, and try to produce data from that. At the same time, given the actual condition that we have right now, which is everyone is dealing with with the COVID-19 pandemic, we connected the dots, and it is a similar condition to the application field that we have. It is a medical condition that affects a lot of patients all of a sudden. It is in a similar field as ARDS, where it affects the lungs mostly. It is visible through the lungs. And it is mostly through the experience gained in the Smith project and through data provided through other partners, which is part of the European Open Science Cloud. The eHealth line is providing medical data. Forschungszentrum Jülich is providing the mechanical know-how, the scientific know-how, and the University of Iceland is providing the manpower, because right now we have also a master's student who's working on this. He's in the corner of the room. I'm going to spotlight him for a second. Gisli Ingolfsson. So this work is also, since it is in the same field, it is in the same direction as the work that we are doing with ARDS. So we can apply the knowledge that we have, but also this is a research application which has a real world applications. We can actually help in diagnosing ARDS in a way or another. We can apply it also eventually to a broader range of applications, because in this case where we are using chest x-rays to be able to diagnose a disease, since we already know that ARDS specifically is exhibited as ground glass textures inside the lungs, COVID-19 is exhibited slightly differently with infiltrates, as we've already heard in the news, but also slightly differently. There is this COVID net, which is a not artificial neural network, actually convolutional neural network based on residual networks that is able to accurately diagnose conditions based on images. It is trained on pneumonia, pneumonia, COVID-19, and normal patients, so it can detect which is which. But using the data that we have and the machine learning knowledge that we have, we can transfer the learning into other conditions. So with that, we come to the objectives that we're trying to achieve with my project. They are 5 objectives. The main one is to understand ARDS, how it is happening in the patient, what it can lead to, and how we can treat it. The second objective is to explore machine learning models for ARDS, in which we apply time series prediction and deep learning for the detection of ARDS, but also for prediction of direction that the patient is going in. We explore mechanistic modeling for ARDS patient simulation, which is our application of the simulator provided through our partners. We explore machine learning models for COVID chest X-ray images. And finally, we apply the available architectures at the ULISH Supercomputing Center to accelerate this work, to scale it up, and to see how further we can take it. All of these will go into details, and we'll go into them in detail in the next slides. But mostly, this is the outline of my thesis. It begins here, and it goes through all of the steps iteratively. But also at some point during these two steps, we have to jump forward to the last objective and then come back. But mostly we have to start somewhere. So we have to start with a lot of literature review to understand the use case. And I'll go into further details in this, but I'll leave it here for a second, just so like you can admire the beauty of the colors.
It's a very good overview.
With that in mind, this will shrink to this size just so we can keep track at which point we are. So we are currently at step 1, where we are at ARDS understanding. So the first thing to do is understand the use case through literature review, but also we have to understand the data that we have access to. The data we have access to is the MIMIC3 database, which is an open database available for research purposes. It's data collected over the scope of 10 or 12 years from the Beth Israel Hospital in Boston, if I remember correctly. Sebastian, correct me if I'm wrong. But there's also access to the UKA ISA database, which is more closed and more private, and we're leaving it to the last minute for also researchers from the UKA to be using. But mostly having access to it, it means that we have access to current real-world data. And some of this data is also from COVID-19 patients, because research opportunity. So with that, by joining the understanding of the use case and the understanding of the data, we can identify the potential applications for our research, what we are going to apply, but also how we are going to apply it. And of course, to be able to do that, we have to do a lot of literature review of what has been done. And I think I've summed it up pretty well in the beginning of the presentation. The next step is to apply machine learning for ARDS. And that was part of one of the courses that I took, which is the deep learning project with, don't exactly remember the name, but Magnus, I think. Yeah, so in that course, I applied some prediction models, the deep learning model mentioned here, and a sequence model also, but I'll get to that in a second. But mostly I started with understanding the data specifically using PCA, reducing it to the most relevant parts of the data. Because of course, the patient, the data collected from the patient has about 43 different parameters that we are looking at over time. So if the patient stayed for 10 days and there's recording every 15 minutes, we have a lot of data over 43 parameters that some of which are not relevant. We maybe don't care that much about heart rate if we have information about how much oxygen there is in the blood. That would be more relevant. So by using PCA, it narrows it down to to variables, let's say 5 or 6, that grow and change more rapidly, more effectively to show the change in that patient. From there, we go into clustering the patients using, in my case, I use DBScan, but the fellow researchers at the Uniclinic Aachen applied different approaches to clustering. And in other cases, I applied data prediction. This is the course I was mentioning with Magnus, where I tried sequence models, artificial neural networks, recursive neural networks. In this case, I used GRUs and LSTMs, and also deep learning models. In this case specifically, I used one-dimensional convolution, which can be, operates similarly to convolutional networks used in image processing, but also since it's one-dimensional, it can follow through linear data or time sequence data. So it is very good at also predicting. And one of the papers that I published mostly highlights this part of my research as an application field of the work that is being done. Third step of the thesis outline is machine learning for ARDS simulation. So we have access to this simulator, the Nottingham simulator that is provided through our partners. We have to understand it because, of course, this is code written by other researchers, not very well commented, and I have some opinions about that. But you have to go through it, you have to understand how it works, because also my fellow researchers at UKA had access to the medical data from their hospital. So they had to understand it as well to be able to create new data to run through that simulator. So we work together to be able to understand it better. We are going to, next step, select the relevant features for the simulator that we care about because it produces every possible feature for that patient after finishing the simulation. What we want, what we care about are specific parameters that would identify if that patient survives or not, gets ARDS or not, gets better or not. And from there, we are going to design and build a new model, either based on artificial neural networks, CNNs, or RNNs. And all of this decision-making here is going to happen based on the knowledge that was gained through the other thesis objectives. I'm pretty sure that artificial neural networks will not be part of it, but this is worth mentioning because we have to go through the process of understanding all of the possible applications and then trim them out one at a time. It is worth mentioning here that at this point, I am at this decision process here, but at the same time, I'm also in this, going through this process with Easley. This is where we have data from the partners in the EOS, in the European Open Science Cloud project, where they provide data, eHealthline mentioned here, but there's also access to the COVID-X data set, which is an open source data set of chest X-ray images. We have to understand and analyze this data. We also have to understand and analyze the model, which is the step that we were currently struggling with until last week when we kind of hit a new opening. Based on that, we have to, based on the understanding of these two parts of the project, we have to select the best model that will produce the best results. In this case, selecting the best model is based on Gisli trying to identify which parts of the COVIDNet deep learning model is more effective at analyzing the new data that we have. Because they mentioned in their research that COVID-X works best with their higher end model that has 480 by 480 images. But as Gisli discovered in his data, the images are much smaller in the eHealthline dataset. So we had to use a smaller model that performed relatively well, but not as good as the one that they used in their research. So in this case, selecting the best model is effective, is necessary. And from both of these objectives, I put them in parallel because they are happening at the same time. So machine learning for ARDS simulation and also machine learning for COVID-19. We jump into the final step of the thesis outline, which is the speed up and the scale up. So in the case of the COVID data set, we currently finished parallelizing inference, producing results as fast as we can, and highlighting the effectiveness of using high-performance computing to create outputs to test the network. So we managed to show that inference in parallel produces more results. It is better than running it in serial. It's also better to run it using high-performance computing in the first place, because running it on computer took about 40 seconds for each image. In serial, on the high-performance computing node, it took 20 seconds, and in parallel, with several running at the same time, that means 20 images can pass at the same time. At the same time, we did compare results from the data sets. So we compared the output for COVIDNet for the COVID-X data set that was provided with the data, with the network, but also with the new data set from eHealthline. Gisli discovered some minor details about his data, and he was very successful at rectifying it very peacefully. We didn't have to break anyone's arm, luckily. And he managed to produce results based on the new data set. And we found that it is not as accurate as the original data set. So at this point, we have to retrain the model. And we can retrain it locally, but it's very slow, as he found out. So what we can do is apply the knowledge in machine learning and parallel GPUs to be able to accelerate the training process, which is currently the step that we are doing. At the same time, using the simulator provided by the partners in the ARDS project, we can generate new training data. In this case, training data means the input that we are giving to the simulator generated recursively with the assistance from the UKA, but also the output from that simulation. So we have a lot of input, a lot of output, mostly because we will be running this simulation on the cluster at Jülich. These inputs and outputs will be used to build, develop, train, and test a new model that's based on machine learning, probably recursive neural networks, and will be tested. And finally, as the last step of my project, this model will be deployed, hopefully, in hospitals in Germany to test it out, because, of course, the simulation itself is too large and too slow to be able to be used at hospitals. And also slightly closed source, they made it clear that they don't want to share it. So with that in mind, these machine learning models and COVID-net model will be trained and tested or retrained and tested on the supercomputing cluster at Jülich. Currently, I am using the deepest, cluster, I'd say, but we also have access to the Joule supercomputer, which is currently the fastest supercomputer in Europe. So by the time we can achieve some scale up here, we will definitely be able to achieve that like miles beyond that scale up in joules. And with that, we get to a short description of the blueprint that we set up as part of this project. I will not go into the details, but I'll mostly concentrate on this part here, which is the application of key hardware technologies, libraries and packages that are efficient, that are adapted to the project that we have, innovative computing resources. In both cases, the supercomputing architecture, modular supercomputing architecture at Jülich, but also portable container environments that can also be applied in the cloud. As I mentioned before, the vendors public vendors or private vendors available. All of these as part of greater overarching projects or communication or data sharing projects for the applications in this case, ARDS time series analysis and COVID chest X-rays. But also, at some point, we started working with the Canadian C-brain infrastructure for the neuroscience and big brain research, which is an analysis of brain slices that are provided in cooperation by the McGill University, if I remember correctly, and the Jülich Supercomputing Center. So this is a brief architecture of the work I am doing in terms of the work I have done in terms of the project, the medical project. And with that, on this side, we have a brief description of the work that is being done, but it's not very much in detail. But with that, we get to where I am right now in terms of the midterm. So in terms of at the midterm status of my project, I started at July 2019 with my PhD. So far, I have finished 3 courses, which are the deep learning course with Magnus, the cloud computing and big data course with Professor Morris Riedel, and the text analysis and rhetoric for PhD students with Randy Stebbins, which was a very necessary course in terms of analyzing the literature for this project. It was interesting because in a way you can understand the words that they use to describe the work that was not done. At the same time, there was parallel work being done in the On-for-Off project, which is a project for retail. In this case, this project is for, the work done in this project is not counting towards my thesis, but we did get a publication out of it. And these are machine learning transfer applications because they are applications of image processing, association rule mining, and collaborative filtering, which I believe have some potential in being used in medical applications. Find underlying associations in several conditions or underlying associations between parameters within the same patient. I am expected to end my PhD in 2022, if COVID allows it. And with that in mind, I will have publications in terms of the medical infrastructure work. I did have publications about that already and the retail infrastructure work that is being done, and it is mentioned in this slide here. It's similar to the slide before, but it's more towards the retail applications. But also, there are planned publications on the COVID work being done currently. This is going to be a joint publication with Gisli, of course. And he will also be writing his thesis about it. At the same time, we will be publishing about the work on the simulator, which is both converting the simulator from a MATLAB application towards a machine learning application, but also in parallelizing and in running it in parallel, but also in producing results in parallel. So the collaboration with the UKA will produce several, I believe, publications in this direction. And with that in mind, and mentioning the work being done and the retail project, which is currently ending, I think we are at the end of my presentation, and I thank you all for your attention. So nobody sues me, but I will welcome your questions right now if you have any.